So let's review a horizontal projectile motion problem. So what we have here is a ball on the ledge of a cliff. Let's say that this ball is traveling 20 meters per second off that cliff. And this cliff is 50 meters tall. Typically, these kinds of questions, you'll be receiving the initial horizontal velocity and the height from which whatever the object is falling. So the questions that you usually get are, what is the ball's Vx when it lands? How long is it in the air? And how far away is its landing point from the cliff? Well, first things first, it's important to remember that a projectile in the air moves in a parabolic path. That's because as this ball's moving 20 meters per second to the right, when it comes off the ledge, gravity starts to take effect and pull it down. And as it's falling, it kind of looks like this. And X marks the spot. That's its landing point. And what's actually happening is every second the ball falls, gravity pulls it down a little bit more, a little bit more, a little bit more, finally a little bit more. So remember, gravity kind of looks like this, orange. So the acceleration of gravity is going to pull this ball down at a rate of 9.81 meters per second squared. So the ball's velocity will start to move downward 9.81 meters per second squared every second. So its initial velocity off the cliff, its initial Vy, is going to be 0. So here, Vy equals 0 meters per second. But after a second of falling, Vy is actually going to start to kind of look a little bit more like this. V1, I'm going to say velocity y at 1 second is equal to negative 9.8 meters per second. It's because it's been falling for a second. And if you kind of work out your velocity equations using acceleration, it'll be about negative 9.8. If you look at velocity y at second number 2, it should be about negative 19.6 meters per second. I should have moved this guy over a little bit. Let's take this number, switch it over a bit, and the arrow becoming a little more downwards. At V3, we add another negative 9.8 to the our values over here. It's something sort of like this. So let's do minus 9.8, so negative, minus 9.8 equals 19.6. We have negative 29.4 meters per second, and the arrow is going to be a little longer. And then finally, it should be at the 4th second, negative 39.2 meters per second. I'm making up these the amount of time this ball's in the air. I honestly do not know if it's 4 seconds or just 1 second. I'm just trying to demonstrate here the effect of gravity on this ball. We will be finding time, but this is what gravity is doing. In the meantime, the initial velocity going horizontally to the right, that doesn't change. That's because there is no acceleration on the right. Gravity works on the y-axis. The x component just remains to be 20 meters per second the entire trip. 20 meters per second. 20 meters per second. Gravity is not affecting this thing along the x. 20 meters per second. So when you get a question like, what is the ball's Vx when it lands? The velocity horizontal when it lands is the same as when it began. It's 20, oops, I'm trying to write a little bit meter, 20 meters per second. There's number one. Ooh, that was weird. Okay. Now, this only works if we ignore like a lot of real-world components like air. Air provides air resistance, and it slows down a ball moving horizontally. Think about throwing a balloon. If you threw a balloon, it doesn't actually go very far, versus if you threw a baseball. It's because a balloon experiences a lot more air resistance than a baseball does. Or the effective air resistance on the balloon is greater than on the baseball. If you threw the balloon in a vacuum, well, one, would probably explode, but if you can keep it from exploding, you wouldn't experience any air resistance, and that balloon would move just like a baseball. Okay, so let's take a look at number two. How long is it in the air? Well, it's in the air. Well, the amount of time it's in the air depends on those vertical components. It's y. That's because the higher an object is from the ground, the longer it'll take to fall. Imagine if this ball was 1 centimeter off the ground. If this thing was 1 centimeter off the ground, it's not going to take very long to fall at all. It'll fall rather quickly, right? If we're 1 centimeter away, it's going to move pretty quick down. If we are 50 feet away, it's going to take a long time for this ball to hit the ground. So let's look at those y components. And that also brings us to another really important point. We must always, always, always treat velocity, or not just velocity, any y and x components differently. They do not mingle, they do not mix, because they are very different. They operate on different planes. So it's very, very helpful to draw out a chart where you have x components. So let's put x components over here. Let's put y components over here. And let's throw time in the middle, because time is going to act like the bridge between these two sides. So here's x, here's y, and let's put down some components. We are given two things. We're given 20 meters per second to the right. That is its velocity along the x-axis. It's going to be 20 meters per second. We're also given the height of the cliff. So it's going to be the distance y. That's going to be 50 meters up. However, the ball fell 50 meters. So the change in displacement really is negative 50 meters because the ball fell 50 meters, right? So a few other things we know. We know acceleration. Acceleration along the x-axis is 0. It doesn't experience any acceleration. It's moving at a constant velocity. However, acceleration along the y-axis is gravity. It's equal to 9.81 meters per second squared. And again, it's negative 9.81 meters per second squared because gravity is pulling downward. And again, negative and positive directions are kind of arbitrary. It's just important to remember that if we call anything moving upwards positive, which is convenient, that makes the most sense. That's kind of how we live our lives. Up is usually positive. Anything moving downwards would be negative. So the negative symbol here is just suggesting it's opposite of whatever positive is. And normally we call up positive. So let's just have a policy where we call down negative. We know more. That initial velocity coming off the ledge, that initial velocity y, that's going to be 0 meters per second. So now that we have these three components here, we can pretty much find everything else we ever wished to know about the path of this ball. So again, we were given two components. We're given its horizontal velocity, and we're given its height, the height of the cliff, the height of the fall, the distance this thing fell. With just these two components, we can calculate everything else. So first things first, we're looking for how long is this thing in the air? What is the time? We're looking for the t. Now, if you review your equations, you can use distance is equal to VIT plus 1/2 AT squared. When we work this out, we're going to use the distance of the y is equal to the velocity initial along the y times t. Because t, there is no y. Time does not operate on a plane. Time does not operate on an x-axis or a y-axis. Time is free of all that. You don't go 8 seconds left, 2 seconds down. When you're providing time to somebody, you don't condition it with direction. You will with velocity or with distance. If you're giving directions on how to get to a place, you might suggest you're going a block north or like 3 feet down the hall, but not with time. So if we finish writing out the equation, it's 1/2 a y, again, because acceleration is a vector, there's direction to it. And again, t squared, it's free of y. T operates on its own little world, scalar world. If we substitute some values here, we'll find that the distance y is in negative 50 meters. The velocity initial y is 0 meters per second. We do not know time. Plus 1/2. A is negative 9.81 meters per second squared. And we don't know t squared. 0 times t is just 0. You're left with negative 50 meters. It's equal to 1/2 times negative 9.81 meters per second squared. My bad, this way, close parentheses, times t squared. To get the t squared by itself, we divide on both sides. Let's divide 1/2 times negative 9.81 meters per second squared. Divide here, 1/2 times negative 9.81 meters per second squared. These guys cancel out, and you'll have to t squared by itself. So that should look like this. Actually, let me see if I can move all this out of here, because this is getting a little clunky. Here, let's see if we can do this. Here we go. Let's throw these into the mix too. Okay, having a little difficulty here, but I think I got it this time. There we go. I'm going to just drag these guys out over here. There we go. Okay, so now negative 50 meters over 1/2 times negative 9.81 meters per second squared. Forgot the one there. Equals t squared. To get t by itself, you just take the square root. So t equals square root of negative 50 meters over 1/2 times negative 9.81 meters per second squared. So I'm working out everything and showing each step of my calculations, because I know sometimes that can be kind of confusing. And let's plug it in. So 50 negative divided by 1/2 of negative 9.81 is 4.905 negative. Now look at it's 10.19. We must take the square root. It's going to be 3. T equals 3.19. T equals 3.19 seconds. That's the answer to 2. And that also goes here. 3.19 seconds. Okay. So far, so good. One more to go. How far away is its landing point from the cliff? Oh, and also just to kind of clarify here, there is no 4 seconds, right? I was estimating all these purple values along the y-axis, so technically this region never hits velocity at 4 seconds, and that's okay. So let's find out how far away it is from the cliff. Now its distance along the x, this thing here is what we were looking for. We were looking for this component here. How far away is it from the x, from the cliff, that x distance? So let's look for dx. So notice again, I'm not mixing and matching anything on the left and the right. I'm only working with values on the right and only working with values on the left. Only working with y vectors, only working with x vectors. And the only bridge is time. Time is like the value I can use to extrapolate information like that distance x. The way I would do that is by looking at velocity is equal to distance over time. This is average velocity. And technically, like, we can use this because there's no acceleration. Acceleration is 0. So if we're going to get distance by itself, you can multiply t on both sides and you'll get the distance along the x is equal to the velocity x times time. This works out nicely. And in case you weren't sure, why are we using this equation as opposed to distance is equal to VIT plus 1/2 AT squared? You can use this equation. It absolutely works. And if you remember, acceleration is 0. If you plug in 0 for acceleration, you'll find that all of this stuff gets canceled out because a is 0. And you're left with d equals VIT, which is the same thing as this equation, which is the same thing as that equation. So let's work this out. Let's put in a value for dx. We don't know. Let's put in a value for vx. It's 20 meters per second, this thing here. And the time, if this thing was in the air, was 3.19 seconds. So 3.19 seconds, or 3.19275 times 20 meters per second is 63.85. The distance along the x is equal to 63.85. Let's round it to 86. And technically, if we're using significant figures here, I really should be rounding it to just one digit, but that's okay. 63.86 meters. 63.86 meters. I'm going to kind of move this work over. Move these guys down here off to the right, off to the side. Okay. So we're like too cluttered over here. 3.86 meters. Great, we're done. I'd like to just discuss a few other points. We can find how fast the ball was moving when it landed. So how fast the ball is moving when it lands takes into account the fact that, let me just redo what I just did there. Did that work out okay? Yeah, it did. This ball has an x and y component. If this ball has an x and y component, its final speed, its total speed is a combination of the two. It's the resultant. So if this ball is moving a velocity down and it's moving a velocity right, the resultant of these two velocities is down to the right. And the way you can find out what that resultant is by using Pythagoras. And also, first we need to figure out this final velocity along the y-axis. And then we could figure out the final velocity, the actual final velocity. It's final velocity on the y and the actual resultant final velocity. So to find out the final velocity on the y, there are so many equations you can use because we have so much data at this point. I would go with the simplest route. I personally think Vf is equal to Vi plus At is the most obvious way to go. So Vf, let me scooch all this over. There we go. We're solving for Vf, and this is the Vf of y. It's equal to the Vi of y plus the A of y, and again, t is scalar. There is no vector along with that. So we're just, again, using the y side. We do not use any of these x components here. We're only using the y side. So Vf of y is equal to 0 meters per second, right? That's the initial velocity on the y side, minus 9.8 meters per second squared, right? That's the acceleration on the y side. I really needed to give this some more space here. I'm not doing it justice. Scooch this over. All right, I think that's okay. Okay. So don't forget time times 3.19 seconds. Now, negative 9.8 times 3.19 seconds. 9.81 negative times 3.19 seconds. We have a final velocity along the y-axis of negative 31.29. Sure. Meters per second. Vf along the y is negative 31.29 meters per second. And again, it's negative because it's going down, obviously. So now we have our final velocity along the y, negative 31.29 meters per second. And we can find our resultant by using Pythagoras, because on a right triangle, right, a squared plus b squared is equal to c squared. So to get our final velocity, our total velocity altogether, we're going to do a squared plus b squared is equal to c squared. Or in this case, the velocity x squared plus the final velocity along the y squared is going to give you your total velocity, your final velocity, regardless of whichever dimension, if we're talking about y or x, like the combination of these two things squared. So Vx squared is 20 meters per second squared plus Vfy squared we calculated to be negative 31.29 meters per second, right, squared, is equal to the final velocity of this thing squared. Now, this number squared plus 20 squared gives you 1,379.3. 79.3 meters squared per second squared, because that's what happens to units when you square them. And it's going to equal Vf squared. Take the square root on both sides to get the Vf by itself. That's a terrible square root drawing. There we go. Finally, Vf is going to equal 37.14 meters per second. So the final velocity here, this thing, is equal to 37.14 meters per second. So that's a combination of the velocity along the x and the velocity along the y. Hopefully that makes sense, because if you also just look at this drawing, obviously this makes a hypotenuse, and the hypotenuse is going to be the largest side. You have one side that's 20 meters per second, and another side that's about 31.29 meters per second. 37 looks pretty good. And that's, I mean, this honestly is pretty hard for Regents level, but just to kind of show you everything that we could potentially get. And we found all of this out with, just again, a reminder, we were only provided two numbers, velocity x and the height of a fall. And with just these two numbers, we were able to find everything else regarding the trajectory of this projectile in motion. I hope this helps. See you in class.